Hi everyone! In this video I would like to talk about cyclomatic complexity. We've talked about unit tests a couple of times in this sequence of videos, and so I just want to remind you here that unit tests are looking at small parts of your code, usually individual methods. And when you're thinking about having good testing, you should look at your code and consider things like how many different paths can I take throughout my source code. For example, if I have if statements or booleans, then I should check what happens if they're true and what happens if they're false. I should see what happens when a loop starts or ends, or if you don't go into it at all. And so these sorts of things are useful to check to make sure that you're testing basically all paths in your code. So that is what we are doing, basis path testing, when we write our unit tests. And we want to test all of the possible ways that you could run through a particular piece of code, which for us is generally just going to be a single method, right, for unit testing. Now, one visual way to figure out what those paths are is to draw a control flow diagram of what's going on in your code. The control flow diagram is a pictorial description of the flow of program control. Diamonds are going to represent decisions, and rectangles are going to represent program statements. And there are certain rules about how you draw these control flows. You would want to break apart compound conditionals, and things like loops have one decision, which is whether you continue or not. So this is just to give you an overview. It will make more sense when we look at a couple of examples of standard templates. So let's take a look at a couple of different control flow templates that are pretty standard for different chunks of code that you might write. For example, you might write a for loop. And so if we look at the control flow for a for loop, you have whatever's going on before the loop starts. And then you come to this decision diamond, which is basically saying, I have some sort of way of iterating through my loop, and I want to check if a condition is true. If it is, you will go into the loop body and execute it. And then you will go back up and check again if that condition is true. When that condition becomes false, you will leave the for loop and then continue on beyond the loop to any other part of your code that exists. So you can connect these kind of like blocks. Let's look at the if statement. Here we have a diamond, and if it's true, we will execute a certain statement. And we only need to do this once. If it is false, then we don't go through the if statement body at all. We just go to whatever's after it. That is the same thing that's going to happen after we execute the if statement. So either way, these arrows end up pointing to this block that comes after the if statement. In contrast, the if-else statement has a block that will execute if it's false and a block that will execute if it's true. And there's something that happens at the end after all of that is done. You can keep building these up. So I have these nested if-else statements where you can follow these diamonds and see what's going on in terms of being false and true and see where you end up. You can have a sequence of if statements that flow one right into the other. And so all of these just indicate different ways of drawing your code. You could literally take your code and then put your if statements or your for loops into these diamonds and then put the statements that go along with them inside the bodies in the rectangles. Let's look at a couple more examples to understand a little bit better what's going on with these diamonds. So here I have some compound predicates. When you have a more complicated thing inside your if statement, you want to have more boxes. So if value 1 and value 2, then I have this box right here where if both diamonds are true, then I will do something because that lets me go into the body. And if either of the diamonds are false, I do something else. On the other side, I have if value 1 or value 2, where if both are false, I'm going to continue to do whatever this statement is. But if either are true, then I will go into this block that allows me to go inside my if statement body. Right? So in this case, I've broken out some slightly more complicated if statements. And one thing I will mention here is you'll notice that for the and statement, if the first thing I see is false, then I can leave my if statement. I don't even have to check the second one to continue. And similarly for the or, if that first diamond is true, I can just continue on. I don't need to check the second diamond. And that's because of something called short circuiting. Okay, so here I have similar diamonds and rectangles to what we've seen before, only now I've put some text in there to just kind of show what's happening. I have a while loop on the left-hand side of the slide and a do while loop on the right-hand side of this slide. And in both cases, the diamond is just checking, is the test true? And then if it is true, then it will execute a controlled statement. If not, then it will execute a statement after the loop. And this is the same thing for both of them, but the difference is, of course, that a while loop is not going to execute the statement at all if the test is never true, but a do while will execute the statement if it's true at least once. If the do while will execute at least one time. Good. Here is a for loop, and what I've done is I've kind of broken this up a little bit more to show what's going on, where here I'm checking if a test is true, and if it is, I go inside the for loop body and I execute the control statements, and I'm also going to perform an update, right? So that update actually occurs inside the loop, and then we go back and check if the test is true again. The second it becomes false, in other words, no, we are going to execute the statements after the for. So let's talk about cyclomatic complexity, which is purportedly what this video is about. When you draw your control flow diagrams out, you can now determine the cyclomatic complexity, which is, given that my code looks like this, what is the minimum number of test cases that are needed to test the method comprehensively? The lower your complexity, the easier it is to test, and also usually the code is more understandable. Right? So putting this all together, cyclomatic complexity is just counted as the number of diamonds plus 1. Right? So when I drew all those control flows, it was so that we could decide how many tests we were going to need. We at least want to create a test case for each possible path through the code, and if you've drawn the control flow, cyclomatic complexity gives you the number of paths. I will point out cyclomatic complexity is just an estimate for the number of tests you need. Once we have possible paths, we need to consider input values that will test each of the paths. Creating tests to consider all paths of statements is usually straightforward, but creating tests to consider all paths of loops is more complex. And so here it's typically not possible to think about all the different ways you could run through a loop. So we limit ourselves to some standard ways of testing a loop. If you want to test a simple loop where there's no nesting, where the loop can iterate, let's say, n times, then you would want to consider at least failing the conditional test for entering the loop at all, executing the body of the loop only once, only twice, some random value m, where m is less than n, executing the body of the loop n minus 1 times, executing the body of the loop n times, and trying to execute the body of the loop n plus 1 times. Right, so this way, basically we have 0, 1, 2, some number that you can pick, minus 1, exactly n minus 1, exactly n, and n plus 1 times. And so this 1, 2, 3, 4, 5, 6, 7, these are that's a good amount of testing to see if a loop is working the way that you expect it to. So let me leave you off with an example of if you are given a control flow diagram already, how do you calculate its cyclomatic complexity? Well, I just told you it was the number of diamonds plus 1, so let's just go through this picture. And I come in, I have a rectangle, so that doesn't count. I have a diamond, okay, plus 1. Another diamond, so that's 2. And then another diamond, so that's 3. So I have 3 diamonds, which means that my cyclomatic complexity is 4. Right? Number of diamonds plus 1. So now what you can go through is, now that you know that this is the number of tests, you can think about what those tests are based on the different paths that you have through this control flow diagram. All right, so that's all I have for you right now. Thanks for watching.